Jai Hind dear students, I am Dr. Preeti and today we are going to start with the revision of the chapter Gravitation. Since it's a revision video, we are going to move in points so it's easier for you all to memorize the things. So we are going to discuss about all these things today in this video. So let's start with that. When we talk about gravitation, the thing that comes to our mind is the motion of the planets around the sun, the motion of the moon around the earth. How is it possible? How is it possible that the moon is revolving around the earth? Just let's explain that with the example of a ball tied to a rope. So I have this ball tied to a rope and I'm continuously moving it in a circular motion. The force that is keeping the ball towards the center of the circle is the centripetal force that is provided here by my hands. And if I leave this ball, it will try to fly off along the tangent of the circle and it will try to move out of this circular motion. Let's say. So, here, whenever any object is moving in circular motion, its velocity tries to pull it outwards, but a force has to be there that pulls it towards the center and keeps it moving in the circular motion. This central force is known as centripetal force. When the earth is revolving around the sun, the moon is revolving around the earth, the centripetal force is provided by the gravitational force of attraction of the earth. Okay, so that keeps the earth moving around the sun, that keeps the moon moving around the earth. Okay, so that is how all the planets are moving in a circular motion because of the gravitational pull of another celestial body. Fine. Now comes the universal law of gravitation. Do you know there always exists a force of attraction between any two objects in the universe? These two objects could be you and me. These two objects could be your books and you. Okay, so any two objects in the universe are always having a force of attraction between each other, and this force of attraction is known as universal law of gravitation. Now, how much is this universal law of gravitation? What does this states? So, according to universal law of gravitation, there is a force of attraction between any two bodies in the universe, and this force of attraction is directly proportional to the product of mass of the two objects and inversely proportional to the square of the distance between the two objects. This force of attraction is directly proportional to the mass of the two product of the mass of the two objects and inversely proportional to the square of the distance between the two objects. Okay, if we remove this proportionality sign, then we get F is equals to capital G m1 m2 upon d squared. Then why only we feel this force of attraction between us and the earth? Why don't we feel the force of attraction between us and our books? This is because if one of the object is earth, then see, one of the object's mass that we will be considering here will be the mass of earth, and this will make this force to be considerably a big value. But if we take any other two objects, suppose you and your books, this total mass will be very less as compared to the value of G, because I'll tell you the value of G. What is the value of this G? If we calculate, this was done by the capital value of this capital G, which is a constant, and this is known as universal gravitational constant. This value was calculated by Henry Cavendish, and he calculated the value as 6.673 into 10 to the power minus 11. I'll tell you the unit as well. Okay, so it's very small value. And now if you multiply it with your mass, that is 50, your book's mass, that is maybe again 50, then also the total value will be too small. because the value of capital G is having 10 to the power minus 11, and 10 to the power minus 11 means you are dividing that number, you are dividing that masses, product of the masses, by 1 and 2 with having 11 zeros. Okay, so if the denominator is such a big quantity, then the answer is going to be 2 less, and that is why we never feel the force of attraction between us and any neighboring objects. But we do feel the force of attraction between us and the earth, because the mass of the earth is approximately 6 into 10 to the power 24 kg. So that will make the total force to be really a big amount. Okay, so now we will calculate the SI unit of capital G. That is another very important question for your exams also, that what is the value of this capital G, what is the unit of this capital G. So no need to remember that, just remember this formula and we'll be able to find out the unit of capital G. I can write capital G is equals to F into D square upon M1 M2. Everyone agrees with that? I have just rearranged this formula. So I have to calculate the value of small capital G, universal gravitational constant. So I have just cross multiplied that. Okay, we get for Newton for force, the SI unit for force is Newton, distance is meters square upon product of masses. M1 and M2 both are in kg, so it will make kg square, which could also be written as Newton meter square per kg square. Okay, so you can write this way or that way, but that usually comes as a 1 marks question, usually as an MCQ. Okay, so you should remember both the ways. You should be able to figure out which is the correct option. Usually it comes as a multiple choice question. Okay, so I hope that much is clear to you all. The value of capital G, this capital G is known as universal gravitational constant. And when one object is pulling another object, when one object is applying a force of attraction on another object, that is known as gravitational force. This force of attraction between any two objects is known as gravitational force. Fine. Now, if two objects are applying a force on each other, and if an apple is being pulled towards the earth, does the apple also pulls the earth towards itself? Yes, the apple also tries to pull the earth towards itself. But why is the earth not moving towards the apple, whereas the apple moved towards the earth? Let's see that. You know that. Can I erase it off? Okay, so I can have some space to write. So when the apple is applying a force on the earth, the same force is applied by the earth on the apple. According to Newton's third law, we know that these forces are equal and opposite in nature. So let's find out how much will be the force applied by the apple. Mass of the apple multiplied by acceleration of the apple will be equal to mass of the earth multiplied by acceleration of the earth. So you can see mass of the, even if these two forces were equal, but the mass of the earth is too much, so the acceleration of the earth will be negligible or almost zero. But the mass of the apple is too small, the product is the same. So here the mass of the apple is too small, and so there will be a considerable acceleration that will be there in the apple. So you will be able to see the apple moving towards the earth and not the earth moving towards the apple. Okay, I hope that is clear. One more thing is there. If the moon is being attracted towards the earth, then why doesn't the moon fall on the earth? The moon doesn't fall on the earth because its velocity is constantly keeping it in the circular motion. Whenever there is any circular motion, its velocity of an object that is keeping it in the outward direction, that is keeping it moving in the circular motion. And the gravitational pull of the earth is pulling the moon towards itself, and that is why the moon is not able to fly off in the straight line. Suppose you have a question that suppose if there is no force of attraction applied by the earth on the moon, then what will happen? Then the moon will fly off in a straight line motion. It will be moving on in a straight line motion, and it will not be revolving around the sun, around the earth, if there was no gravitational force of attraction by the earth. Okay, so I hope that is clear. We have to do a bit more question based studies now. When we are coming towards a revision part, you have to just revise what could be the possible questions and what should be your answers for that. Now next is the free fall. What is free fall? Whenever an object is falling towards the earth only under the effect of gravity. Suppose I leave the lid of my pen and it's falling just under the effect of gravitational pull of the earth. Such a movement is known as free fall. I'm not throwing something, I'm not putting any force on that object, I'm just leaving it, I'm just dropping that thing, and it is coming under the effect of gravitational force of earth only. Then it is known as free fall. And you have seen when the lid of the pen started, it was having zero velocity, and when it reached the earth, it was increasing in its velocity because it was having an acceleration. And how much is that acceleration, and what is that acceleration called? This acceleration is known as acceleration due to gravity and represented by small g. This acceleration due to gravity is represented by small g. The capital G was a universal gravitational constant, and it was a constant value wherever you go in the universe, between any two objects in the universe. But this small g is the acceleration due to gravity, and this acceleration due to gravity is how much is the velocity of an object going to change because of the gravitational force of attraction. Okay, this acceleration due to gravity will change from one planet to another, and even on earth it's not going to be constant. I'll tell you how. Okay, so when we talk about this small g, let's see that this small g, how we can calculate that. I'm just erasing this off. So how you can calculate the value of this small g? You know that force is equals to mass into acceleration, and we have also seen that force is equals to capital G m1 m2 upon d square. Now if one of the objects is earth and the other object is any object on the earth, then we can take that the acceleration of that object is equals to mass of that object into acceleration due to gravity. Suppose that object is earth, apple. So mass of the apple multiplied by acceleration due to gravity of that particular apple will be equal to force. This force is also equal to capital G. First object will be mass of the earth because the earth is pulling it. Second object will be that apple. I am representing it with m only, and upon distance. Now distance between the apple and the earth, how we will take that whenever two objects are there, the distance between them is taken as the distance between the center of the two objects. But when one object is earth and the other object is, say, anything on the earth, anything that is close to the surface of the earth, then as compared to the radius of the earth, the distance of that object on the surface of the earth is negligible. So whenever we have to take this distance and one of the objects is earth, we usually take that distance as the radius of the earth. Okay, so here we will be taking the distance as the radius of the earth square. This mass and this mass both are of the apple, so we will get the value of small g is equals to capital G, mass of the earth upon radius of the earth square. All these are constant values. Mass of the earth has a particular value, radius of the earth has a particular value, and so if we put the values of all these things, we will get the value of small g as 9.8 meter per second squared. Okay, so we'll get 9.8 meter per second square as the value of acceleration due to gravity. Okay, which for doing the numerical sometimes we round it up and take it as 10 only. Okay, so for some numericals we will be taking the value of small g as 9.8 meter per second square. For easier calculations, we might also take it as round up to 10 meter per second square. Okay, but one more interesting thing is there waiting for you all, that our earth is not a complete spherical structure. It's just oval in shape. It's not a complete sphere. So the radius of the earth at equator is more as compared to radius of the earth at the poles. Radius of the earth at equator is more and radius of the earth at the poles is less. So what effect that will be having on our G? We have just calculated that small g is equals to capital G mass of the earth upon radius of the earth square. So we know that this G is inversely proportional to radius of the earth. So wherever the radius of the earth will be more, the value of small g will be more. Okay? Wherever the radius of the earth will be more, the value of small g will be less. Sorry if I make a mistake. So wherever the value of radius of the earth is more, the value of small g will be less, and wherever the radius of the earth is less, at that place the value of g will be more. So where it will be more? Since the radius of the earth at equator is more than its radius at the poles, so the value of small g at equator will be less as compared to value of small g at the poles. The value of small g at equator will be less as compared to the value of small g at the poles. Fine everyone? I hope that is clear to you all. Okay. Now, moving on. Last is the equations of motion. Based on this free fall, any object, if it is falling under the effect of gravitational pull of the earth only, then we will be practicing many numericals, and that will be really very interesting to practice all the numericals. But for doing the numericals, we will use the same formula as we have seen in the motion chapter, that is the 3 equations of motion. Okay, so what are the 3 equations of motion? First is v is equals to u plus at. Now wherever we have the word a, instead of acceleration, now we can replace it with acceleration due to gravity. So instead of a, we will be using the value g. Okay, the second equation of motion was s is equals to ut plus half at square. But I told you, instead of a, we can use the value g. And also, when we are talking about gravitation, when we are talking about falling of the objects under the earth's gravitational pull, then instead of distance, we can take the height of the things. Okay, both could are replaceable. So instead of s, we will be having h. Okay, no need to remember these formula. You can just remember those only, and we can just, while doing the numerical only, we can replace it. Okay, now the third equation of motion was v square is equals to u square plus 2as. Instead of as, what we can write? gh. Instead of a, we can write g, and instead of s, that is displacement, we can write the height. Okay, so these 3 formula will be using to do the numericals, and we will do the numericals in the next video of the chapter. Okay, till then, keep practicing, keep solving the things. I'll just shift to sides so that you can take a screenshot if you want of these things. Okay, good day everyone.